Banach. My first degree is in chemistry, even though I teach in philosophy. And ever since in third grade, I discovered that everything was made out of atoms, and that atoms had electrons, billions of smaller particles. And when I went home and told my parents that those little dots, the little floaters you can see inside your eyes, I believe that I alone could actually see atoms. Ever since then, ever since third grade, science has been an abiding fascination and concern of me, and I spent more years than you've been alive teaching philosophy of science here at the college. So I'm very pleased to be able to talk about this with you. In some ways, our subject matter today is one of the more important ones we can have for the course, because the world that we're going through, the world that you live in some ways the clash between two different worlds and two different worldviews. The first was introduced to you last semester when we looked at the Catholic intellectual tradition, the origins of our civilization in the classical civilization of ancient Greece and in Christianity, and the worldviews that come from them. And then there are a set of worldviews that come from the Enlightenment and from the transformation of our world by the industrial and technological revolutions that came from the scientific revolution. So in many ways, all of us jointly occupy those two different worlds, and we call the era that we live in now the postmodern world, and in many ways the abiding concerns of the postmodern world come from the clash between the two different worlds that we occupy, the worlds of Plato and Christianity on the one hand, and the world of science on the other. So I'm going to talk to you a little bit about the scientific revolution and what exactly science is and why it presents some problems, both for the view of the world that came from the classical world of Christianity and for our postmodern reality today. So the scientific revolution, the period that I'm talking about, is about from 1500 to 1700. You can see the main figures that we'll talk about are Galileo and Sir Isaac Newton. Copernicus often gets a lot of press, although you can see he's sort of an outlier, coming almost a century before the others. Anybody remember, or anybody know what Copernicus is famous for?
Say it. Say it. Come on.
That the Earth is not the center of the solar system, it's the sun.
Right, he was the first modern thinker. There were most of the ancient Greeks already knew that, or believed that the sun was the center of the solar system. But Copernicus was the first modern thinker to rediscover the idea that perhaps the sun was the center of the solar system, not the Earth. Although no one would believe Copernicus until Galileo in 1632 would publish his work on that topic, which caused him to be brought before the Pope and the Inquisition and forced to recant those ideas. There's Copernicus plotting out the spheres of the planets around the sun. There's Galileo, and there's Isaac Newton with his discoveries of the rainbow, of gravitation, and of the tides, and of the telescope. We're going to be talking mostly about Galileo, who more or less discovered or invented what we call the scientific method in his attempt to understand what makes objects float and what makes them sink, as we'll see, and to understand the basic laws of gravitation. So Copernicus' revolution was to see that what we're seeing when we look at the sun move across the sky each day is not what we think we see. When you ask yourself, what distinguishes science and your science courses from your philosophy or theology courses, or this course indeed, you may be tempted to say, well, in science we look at things. We don't just sit in our chairs and read books and then sort of think about things in our mind. We actually look at how the world works. And there is some truth to that. We're going to see what the origins of the experimental scientific method is. But in many ways, the origin of modern science came from exactly the opposite. Earlier thinkers during the Middle Ages followed the philosopher Aristotle, who was the student of Plato, and who became, through St. Thomas Aquinas, sort of the official philosopher of the Catholic Church during the Middle Ages. And they all believed that if you pay attention to your senses, you have to see, it's obvious, that the sun is moving and not the Earth. Copernicus wanted us to believe that, in fact, the Earth was revolving around its axis at a speed of about 1,000 miles per hour, so that all of us are zooming right now in that direction at about 1,000 miles an hour as everything in the sky passes overhead. Aristotle thought if you uplift your senses, and this is what our little baby Einstein was trying to show you at the beginning, it seems fairly obvious to us that what we're seeing is the sun moving and not the Earth. It doesn't feel like the Earth is moving. It looks like the sun is moving. We don't say that's a beautiful Earth rotation. We say that's a beautiful sunset or a beautiful sunrise. So Copernicus' revolution was to see, so what is it that's moving when the sun is moving across the sky? The Earth. Just like when my kids were young and we were driving along the road, they would say, oh, look, the moon is moving, as we drove, and they'd see it on one side of the tree, and then they'd see it on the other side of the tree. It was our motion, just as it looks like the trees are whizzing by you. So the first sort of insight, some people even call this the Copernican revolution, of the scientific method was to recognize what Plato said. Remember, Plato's cave said you can't trust this world that you see with your senses. It might be an illusion. So the scientific method is going to say you can't trust the world as it appears to your common sense. You can't trust the world as it appears to your senses. Because what you're seeing might merely be relative to you and might not be the real truth of what's happening by itself. Our first slogan to represent the scientific method is going to be that science separates the relative from the absolute. The motion that we see, only the real motion of the Earth can only be seen from certain points of view. It's only when we fly up into space that we can see the Earth's rotation. Most of the time, what we're perceiving is not the real motion of the heavens, not the real motion of the sun and the stars as they move across the sky. We're just perceiving our motion, and what we're perceiving is merely relative to us. So, science aims at separating out what in our perceptions is real and what's relative. What's relative and what's absolute. Do you know that word, absolute? None of you have any knowledge of this, but someday when you're 21, you might drink some alcoholic beverages and discover that there's a brand of vodka that's called Absolute Vodka. Any idea why they call it that? Yeah, so solute means solution or mixture. Ab means without. So absolute means without mixture. It's just the object. It's just the world out that we're seeing. The science aims at showing us just the world without any mixture of us. The science aims at separating out the truth that's out there from what's really relative to us, our opinions, our feelings, and our motion. And that was the move with which Galileo sort of started the scientific method in his advocacy of Copernicus' theory that it's really the sun that's the center of the solar system and not the Earth, as our senses tell us. There are two other great discoveries of Galileo. You don't need to know these discoveries. I'm just giving you examples of these basic principles of scientific method. But I'll mention them briefly because they point out the other big idea in the scientific method. The first is separating out the relative and the absolute. Galileo also discovered the basic laws of motion on Earth, or terrestrial motion. Newton usually gets credit for this when you all know the story of the apple falling on Newton's head, and he goes, oh, I discovered gravity, or I got the idea of gravity. Galileo had already formulated those laws. What Newton discovered when the apple falls on his head is just that those same laws govern the heavens, that the very same thing that makes an apple fall also makes the planets revolve around the sun. So, if I drop a heavy object and a light object, and Galileo lived in Pisa for a while and worked there, and he had his students drop things, do experiments like this, where he dropped a heavy object and a light object. He would have dropped a cannonball and maybe a wooden ball of the same shape. Which one will hit the ground first? One of the easier questions you will be asked in your college career. Right, so normally we might think, Aristotle thought, and everyone before Galileo thought that heavy objects fall faster than light objects. But Galileo discovered, in fact, that's false. All objects are accelerated by gravity exactly the same rate, independent of their mass. So if I were to crumple up this piece of paper and drop it along with the ball, they would fall closer to the same. Right, does anybody know why the ball beat the paper to the ground last time?
Air resistance.
Yeah, air resistance, right? So it turns out that besides gravity working on this, you can't trust your senses, because what you're seeing when we saw the paper and the ball fall wasn't just gravity, not just the world as it is all by itself. We were seeing a mixture of different causes. We were seeing gravity and air resistance. And in fact, it's actually somewhat more complicated than that, because if I drop this balloon, has about the same air resistance as this. They're both smooth, round objects in a wind tunnel. They would show just about the same air resistance. Yet if I drop the balloon and the ball still hits the ground before the beach ball. Anybody know why that is? I had told you that Galileo sort of formulated the scientific method, coming to understand why things float. Why does a boat float in water, even though if you make a boat out of metal, you've got a metal rowboat? Why does a metal rowboat float in water? Yeah, boy, and do you know what that means? Okay. So that means that the amount of weight of water that the boat pushes out of the way is actually more than the weight of the metal. So in this case, the weight of air that this pushes out of the way is about the same as the weight of the ball itself, or the balloon itself. So it's actually kind of half floating in the air, half buoyed up. So the point is, again, you don't need to know the physics of floating objects, but the point is that Galileo saw that the world is a messy place. What we see with our senses is confusing and chaotic. The job of science is to simplify that chaotic world. You heard of Plato's world of forms. The job of the scientist is to perform experiments that try to simplify the world so that it approximates the purity, the simplicity, and the perfection of Plato's world of forms. And so we call that purifying the appearances. So now we know it's only in a vacuum that objects fall at the same rate. The first thing they did when they got to the moon is drop a hammer and a falcon feather. You may have seen this little video of a famous show.
This is NASA's Space Power Facility in Cleveland, Ohio, and it is
where they took a giant vacuum and dropped a bowling ball and a feather in that vacuum. And see that they actually hit the ground at exactly the same rate. So that should be puzzling to you, right? Because we did the experiment that Galileo did. Galileo did the same thing. He dropped bowling balls and wooden balls up the Tower of Pisa, and the heavier one always hit the ground first. Yet he was able to see, using his mind, that in fact, even though he couldn't do a vacuum, that may be one of the first times we've seen it with absolute clarity with our own eyes, because we had a vacuum chamber large enough. We could see very clearly the real conditions that were causing the objects to fall, because we simplified and isolated and clarified the conditions so that there were no impurities slipping in. Nothing else was affecting the fall of those except for the law of gravity. So the job of science, then, is to separate out the relative and the absolute, to purify the appearances, not to trust the senses, but to try to take and create in this chaotic world a simplified experiment that will allow us to detect how the forms would operate on their own if this world could approximate the simplicity and the clarity and the purity of that world. Another one of Galileo's discoveries, I think you probably have the idea, is that an object in motion tends to stay in motion. But Aristotle thought that wasn't true. Aristotle thought things would go for a while and get to their natural place or reach an equilibrium and then stop. And again, in real life, we don't see things in motion tending to stay in motion. They go for a while and then they kind of stop. Why does the beach ball stop? Again, friction. There's more going on than just the inertia or the force. If, again, out in space, things really keep going. That's why they have to tether the astronauts up very carefully when they go out and walk in space, because they just push themselves off just a little bit from the spaceship. They would just keep moving and moving, for the rest of time without anything to grab on and stop themselves from moving. So again, our senses misled us because of this messy world, because there's always friction and other forces. That's why if you take college physics or high school physics, or AP physics or honors physics in high school, they always in your physics classes would say, imagine you're on a frictionless plane, or imagine that the object has all its mass centered into the center of gravity. So we're going to see that the model is that the real world is the world of mathematical form that Plato described. This is a painting by William Blake, the 18th century painter and poet, who's picturing God creating the world with a compass, the geometrical compass that you used in school to do your geometry. So this is going to be important for us because this scientific method that I just explained, of trying to separate out what's really in the world from what's relative to us, and take us out of the equation, and to purify and simplify and break down the complicated world into its simplest parts, becomes for us in our modern world the model for how reason works and the model for what reality is. So science is a model for what impartiality is. It's objective. It tries to leave us out of the equation. And the trouble is going to be, this is the clash of the two worlds, is that when we separate the relative from the absolute, when we purify the appearances, we might find that among the things we leave behind, when we make our experiments and we have our scientific theories that get rid of all the impurities and get rid of the human aspects, we might find that our scientific theories leave out humanity or leave out the parts of the world that we find most beautiful. That was the Keats quote that was at the beginning that said that Newton had unwoven the rainbow and taken all of the beauty that we find in the physical world, and after we analyzed it scientifically and broke it up into our scientific theories, got rid of what came from us, get rid of all the impurities, that it wouldn't be beautiful anymore. It wouldn't be the same world that we experienced.